Hi everyone. So in this video, I will go through the steps by which the LLMs are made. Now, LLMs have been famous ever since ChatGPT took off in 2022, and now whenever anybody calls AI, they're just referring to the LLMs, and LLMs just mean large language models, and so we look at how exactly these large language models are created, and this is just an overview. Um this is a high level overview, and we won't be going into any deep details. And by the way, this chart was taken from one of the videos created by Andre Karpathy. So credit goes to he or his team, and he also has did a video. It was a deep dive onto the same topic, but this is just an overview. So now the first, so let me tell you the three main steps involved. First is pre-training. Second would be the post-training, and the third is the post-training of reinforcement learning. Now again, so these three steps. The first step, pre-training, would be unsupervised. So hoping you all are familiar with the basic machine learning terms. For anybody who isn't aware of this term, unsupervised means that the the algorithms uh, in the process of training here do not know exactly what to learn from the data provided. So they are unsupervised. They don't know what is right, what is wrong. They're just trying to learn the representations. So they're trying to make sense out of all the data provided. So the first step, pre-training, is unsupervised. Second step, post-training, is supervised, and it's called supervised fine-tuning because the base model has been created and you're just fine-tuning the model. So first, the pre-training unsupervised. Second is post-training supervised, also called supervised fine-tuning (SFT). Then the third step would be reinforcement learning, post-training reinforcement learning, and this is also supervised, and that's why it's reinforcement learning. And reinforcement learning is just a step where I mean it's a method of teaching the AIs where you reward the algorithm more if it's right or if it has taken the correct steps, and you don't reward it, or you can also punish it if it did not take the steps in the right direction. So that's how reinforcement learning works in short. And yeah, so let's go to the first major step, that is a pre-training, and so this is unsupervised pre-training. So the step one would be just get the data. Now this is usually the uh, like the most time consuming step here, gathering the data and then trying to uh, let the model make sense out of this data. So this is would be the biggest and most time consuming step. So first first you guys you will just gather the data, and then you would do the URL filtering. So now since most data is online, we are doing URL filtering here because uh, you get to know which URLs to include and which URLs to exclude, and then you extract the text, and then you do the language filtering so that you can exclude any languages that you don't want to train on. And go for filtering is just an algorithm, and min hash deduplication is just to make sure that you're not training duplicate data. So I mean duplicate data will be present, but just you're going to remove like majorly duplicate data, so on a higher level. And the C4 filters is just C4 is the name of a famous data set, and so C4 filters would apply to that data set. Now the C4 filters and go for filtering like these depend on the LLMs being created, and you could potentially be using some other methods instead of these also, and custom filters. So there's that. So there's custom filters, and there is a PII removal. Um, PII would stand for personally identifiable information. So you will try to remove that. So once that is done, that would constitute the first step. So that would be, now you have the data. So now going to the second step, it's called tokenization. So basically, you'll convert the text into sequence of symbols. So into tokens. Let's say there's a sentence like here, viewing single post from soldiers for the week of dash dash. This entire thing would be converted into just a sequence of numbers. Now, and those sequence of numbers would be in turn converted into binary. Now, the reason why we are doing tokenization is because the training becomes much better when the words are converted into numbers, and learning or the representation learning or making sense out of the data is better than from numbers rather than just the words directly. So tokenization is where you tokenize the words in all the data that you have. So again, step one is where you gather the data and apply some filters and clean up the data. Step two is where you tokenize all the data and convert all the words into numbers so that the computer can understand and learn from it in a better way. And what is step three? So step three is where the actual training happens, where the neural network training happens, and the neural networks are just uh, in architecture. It is slightly inspired from the human neural network in the brains, but not exactly. Uh, they're not exactly trying to replicate the human brain, and so there are many types of methods in the neural networks, and many ways of training model. So here, what they're doing is, so let's say, uh, so how does this neural network training happen? So so now basically we have tokens, like I said, all the data has been converted into numbers, like just like this. So all the data is now just a sequence of numbers. Now taking an example of just four tokens, let's say I view in single. Now the neural network, what it does is it will just train on this, and it will try to predict the next word for a given sequence of uh, tokens. Let's say I let's say like Paris is in dash. So if if a sentence like Paris is in dash comes, the, the predictor would predict France as the most probable uh, prediction, and then any other words like Europe or anything would come next. So the top predictions, among the top predictions, the most probable word would be France in a sentence. Paris is in France. Paris is in dash. So and in that manner, the neural network training happens, and so they're explaining here the same is explained here. So given a sentence like this, I weaving single, the most probable prediction is direction, and then the case, and then post. So the correct answer is a token of this number. So now what are the internals of a neural network? So neural network internals are so basically it will have the input sequence, the actual sequence of data that we have, and then there will be parameters also called as weights. These are kind of like knobs described here, um, and these knobs initially are randomized, so they're heavily randomized. So and so they are highly randomized initially. Okay, so now Again, this is I'm saying like on a high level. Not all are randomized, and some are more randomized than the others, and the degree of randomization does change. But on a high level, the weights are also I mean, the weights which are kind of like tuning knobs, these are randomized, and then you have these giant mathematical expressions, uh, uh, which these weights and the data and these weights uh, are put into to get uh, like a giant architecture. So basically, this would be the transformer architecture. So this is what a transformer architecture looks like on a higher level. The transformer architecture is a key concept in the LLMs that we are mostly using today. Let me tell you how is that. So now the LLMs that we are using today. So the LLMs we are using today are mostly GPTs. So they are generative pre-trained uh, transformers. Now they're generative because they're generating or predicting the next sequence of tokens. Pre-trained because the first step in creating them, literally, that we are going through exactly now, is called pre-training. And transformers because the architecture that is used to learn the representation from the data that is provided is called transformer architecture. And transformer architecture, whose paper was released in 2017, something like that, is a legendary landmark paper, and it really defines all the paths that the AI has taken today. So most AIs today is basically LLMs. Most LLMs are just GPTs. They're generative pre-trained transformers. It's possible that there are other forms of AI, but as of today, these are the most famous ones. So now that we have taken a look at transformers, so this would in the neural network, uh, so transformer architecture would look like this, and we get the data and then weights. That's how it learns the representations. Now, how does it exactly learn? So the step one was again getting data. Step two, tokenization. Step three, neural network training. Step four is would be inference, and inference is where it tries to infer uh, the tokens from the data, and it tries to learn like what is read and what is not. So let's say there is a sequence like this. So for a sequence of just one letter, let's say like 91 represents the, and what would be the next word? So next word would be 860. Let's say cat, something like that. So the cat. So what would be the next word? 287. Let's say the cat is. So the cat is cute. Let's say so, and this is how it tries to learn, and this is a step of inference. Now, once the inference is done, you would go to the next major step, that is supervised fine tuning, which is post training. Now, just a brief information on like what was GPT-2 about. So GPT-2 was launched in 2019, and of course GPT stands for generative pre-trained transformers, like I said, and it has 1.6 billion parameters. So uh, again, it's transformer neural network as it says here. So it's transformer neural network, 1.6 billion parameters. So as we displayed here, the entire thing is a transformer architecture, and 1.6 billion parameters, and the data would have been in terabytes. So and maximum context length was 1024 tokens, which means for training, let's say like this, a maximum of 1024 tokens could be present in the context, and it is 100 billion tokens. So that is would be the that explains the size of the data. So now GPT-2 was created by Karpathy, just for demo purposes on YouTube. You can look it up. Now, yeah. So now, yeah. So what we now have, so after all this is done, after the training and inference is done, what we have is just a base model. Okay, so we now have only the base model. Now the base model is pretty raw. It's like it doesn't know anything. So what are the psychology of a base model? So it's a token level internet document simulator. It's stochastic, it's probabilistic. You're going to get something else each time you run, because it's stochastic, and it dreams internet documents. It's like a it's like a it's like a brain which is fully confused and is fully high. It's like a brain which is fully hallucinating. So it's like a brain which is fully hallucinating. And so, and also the parameters, the model are kind of lossy zip file of the internet, and a lot of useful real knowledge is stored in parameters of the network. You can decide train documents of verbatim. Basically, it would have known some things like by heart. You can use it for applications, translation, by being clear with the prompts. But we can do better. So this is a raw model. What it can do is, let's say you put something like uh, something like zebra is, if you say, like it would put the next sentences from the Wikipedia. So basically, like it's a predictor. So the only thing it does is a prediction. Okay, so it's a predictor. Just base model. It's just a predictor. It's nothing else. It's not your chatbot. It doesn't have the ability to. Well, it does. It can answer everything that your GPT can. Only thing is, it's not specifically fine tuned for that purpose. So it basically has all the answers that your chatbot does, but it doesn't know how to represent them. So base model is pretty raw, and it's not. It's useful, but it's not trained to be a chatbot. So, and that's what we do in the second major step. So we just write the steps here. So first major step, pre-training, and it was unsupervised. Unsupervised. And if we go second step, supervised fine-tuning. Third step would be post-training reinforcement learning. So now what happens in the second major step, that is supervised fine-tuning, and this is post-training again. So the pre-training has been done now, so we are just doing now the post-training. So we'll teach the model how to have conversations exactly. So like if a human says like what is 2 plus 2, the assistant should give answer like 2 plus 2 equals 4. And what is the initiative of list, like that. So why is this? So when a human asks a question like why, the assistant should be answering like because of like that. And it should also say like you're welcome, let me know if I can help you anywhere uh, with anything else, like that. And should a human say like something like out of bounds, something which is not legal or something like that, something questionable. If your assistant is supposed to not answer it, then you should be training here, like that it cannot help with that. So remember that the all the training in all of this training, there will be all kinds of illegal or like harmful information that your assistant could provide. So which means that uh, if you don't do this post training, and if you could basically ask the model to do all kinds of like illegal things, all kinds of dangerous things, and it would be able to do it because it's a fully directionless uh, brain. So by doing this supervised fine tuning, you're able to make it a little bit more useful and make it a chatbot. Now, so yeah, so as we saw in the tokenization step of the pre-training, this is what the tokenization looks like. So basically, give all the tokens and all the sentences are converted into numbers. So and now the so the models are the model which is not yet supervised trained is called a base model, as we saw, and a model uh, which has completed the supervised fine tuning would be called as the instruct model. So as you can see, it would be called like a instruct model. So which is why that like if you're a developer and if you go to like let's say like you're downloading like llama model, say three, uh, but this would be the base model, so it wouldn't know like how to communicate properly. And let's say there is a, I mean, this is just an example. This like not sure if this is these are the exact names. Now there will be another model called llama 3 instruct. Now this is the one which has been which has completed supervised fine tuning step. So and that's why they're called instruct, because instructions has been provided. It is able to instruct you. So now um, so in this also while doing this, the human labelers are also used here in creating the conversation datasets. And the conversation datasets is what we saw here. So to create those exact conversation datasets, a lot of human labelers are used, and so they are taught things like what is helpful and what is harmless, what is truthful, and what are the what is the way in which the uh, chatbot needs to answer like the most like as much unbiased way as possible. So and so so these data sets are created by humans, and that's what it will be trained upon. Now there's possibility of like hallucinations here. So let's say who is Tom Cruise. It would say like during 10 time Tom Cruise is famous American actor and producer, blah blah blah. And but during test time, uh, if you ask like some random non-existent person like Orson Kovacs, it would say something like it would go on with some random letters like Orson Kovacs is a guy in this random like novel written by some random person, which would not be useful. So what you should do is a model should first check if that data, if that if it has any information on the entity being questioned. So let's say like this Orson Kovacs, does it know anything about it, and is the confidence level is at least like minimum threshold. So if it doesn't have if it's not confident enough about the question being asked, then you should say that I'm sorry, I don't have any information on this. So this is another use of doing SFT. If you don't do this, like a base model would just go on hallucinating that this is some known fact. So this is one of the key things that you would do here. Or like checking its knowledge and confidence levels about that information is one way. The second way would be to allow the model to search. Maybe there is a person called Orson Kovacs. Maybe the model doesn't know it. model wasn't trained on everything anyway. So it should be able to use tools like internet search, which nowadays like all models can do internet search. Before it, like the initial GPT models uh, were not capable of internet search, but now they are, most of the models are able to do internet search. So, and even on the internet, if it doesn't find valid evidence, it should be able to say that there doesn't seems to be like a famous person named Orson Kovacs. Or if it does find it, it can just say that Orson Kovacs appears to be a blah blah blah. So uh, yeah, so the Swiss cheese model of LLM capabilities of current models. So some things work really really well, some things show brittleness. So yeah, and avoiding hallucinations is one of the key uses of doing this, and it's able to do conversation. And now another, so there are some other problems with this. Let's go through that. So vague recollections versus working memory. So knowledge and the parameters are vague recollections, and knowledge and the tokens of the context window are working memory. And so when you provide let's say like a document, like a PDF of some textbook, the model is able to better answer your questions compared to asking it something from its vague recollection, because obviously in vague recollection the facts are not fully uh, like it's not like it's basically vague. So it has to recollect from the vague memory, and trying to recollect from working memory would be more efficient. And let's say like your LLM needs to be like a support assistant for your company, then you'd be better to provide the company documents in working memory. So that would be useful instead of just training it on the documents and then asking it to do vague recollection. So that's another way SFT is useful. And again, knowledge of self. A base model doesn't know. Like if you ask, "Who are you?" to a base model, it would answer some random things on whatever it was trained on. Like I am some blogger, or I am some vlogger, or I'm Chat GPT, like that. If it was trained on data from the Chat GPT, so the knowledge of self can be given in this SFT step, where you say let's say like you are at Google and you're trading the next Gemini, and here in knowledge of self you will say that you are Gemini, and you are a product of Google, and we are created by a team of engineers at Google, DeepMind, and the things like that. And so that when the Gemini is productionized, and when a customer asks like who are you, or what's your name, and where do we come from, it's able to answer from this knowledge of self that it's Gemini and all that. So again, it could be done like hard coded conversations in the conversation data, or it could be a system message. So it would come at the very beginning of the uh, model's instantiation, and that is a slight technical, like a system message or a user message. They are the different concepts. Now, so leaving that technical thing aside, so let's come to models need tokens to think. So I take this example where the human says Emily buys three apples and two oranges. Each orange costs two. The total cost of all the fruit is $13. What is the cost of apples? So now, uh, if you don't train the models to think, it will just repeat like the answer is $3. This is because things like this. But if you have trained the model to think properly, then it would give the correct answer. And so uh, this is also like one of the like important aspects in this step here in this safety step. So and so models cannot count. So these are some of the major drawbacks. Let's say like drawbacks. Models basically cannot count. They don't have so the models are again they are like stochastic people predictors basically. They don't have any tools like a calculator or anything. They cannot count. They can be hugely wrong on counting and doing basic aptitude stuff. But like nowadays, they are pretty good at these things. So and also they are not good with spelling because remember that they see tokens that are not individual letters, and they and some other things like which is bigger 9.11 or 9.9. Most models would give the wrong answer, but nowadays this has been improved because this is a popular problem. This is a very famous issue. So they also they can use tools like code or web search. And just as a revision, the transformer just does the token prediction. So in some input is given, it just predicts the next sequence of tokens, and that completes the second step. That is the supervised fine tuning method in the post training. So we did pre training and post training, supervised fine tuning. Now we will do post training reinforcement learning on top of this SFT model. So now in the base model, it was just internet document simulator. Okay, the base model just internet document simulator. But now, after SFT was done, it's far like a little more helpful assistant trained by SFT. So it is like an assistant now. So now, what more is needed now? So basically now, uh, so all the pre-training was like exposition. So let's say there's a student, you, you will give the student to read the textbook. You will expose the student to the textbook knowledge, all the background knowledge. That would be the pre-training. Supervised fine-tuning would be like working on the uh, worked out problems in the textbook with the demonstrated answers. So it has gone through the text material or the background knowledge in the first step. In the second step, it will go through the worked out examples where it will have both the questions and the answers, and it will study how to answer them. The third step, the major step, is reinforcement learning. Now this is like an actual test or an exam where it doesn't have the answers, and it will just have the questions, and it will try to answer them. And using reinforcement learning, you will do the you'll make the model better basically. So as I already explained how reinforcement learning works, basically when the model gives better answers to the test questions, you would reward it, and when it doesn't, you would not reward it, or you could punish it. So yeah, so I mean this pretty much explains the all the process. So first step, second step, like first step, second step, worked out problems. Third step would be the exam. So and so now reinforcement learning also discovers thinking on cognitive strategies, and you could make it learn new things there. And so let's say so uh, there's a concept of RLHF, and the full form is it stands for reinforcement learning through human feedback. It's so this method was invented by uh, Amade Dario. So I mean, not sure of the full name. So basically, he's the founder and CEO of Anthropic, the people who created Claude and Cloud Code and all those models from Anthropic. So he's the one who created. No, he was also part of OpenAI, and that's when he created this this method to teach these models and make these models better in providing answers. So RLHF. So what RLHF does is, uh, let's go through what exactly RLHF does. So through feedback, we are improving the model, and we can run RL in arbitrary domains, even in unverifiable ones. This improves performance of the model due to discriminated generator gap. In many cases, it's much easier to discriminate than to generate. So, what are verifiable domains? So, verifiable domains are like maths or physics, where the answer is definite, and unverifiable domains are when there's no facts and which poem is best or things like that. So, and RLHF works in both cases, and that is an upside of RLHF. So the downside would be that there's a lossless simulation of humans. So it could be misleading. Let's say if it discovers a way to game the model, like it discovers like adversary examples of the reward model, like even after like thousand updates, the top joke what pelicans is not the banger you want, but something totally nonsensical like the. So uh, if it finds a loophole, then RLHF could be dangerous, and it could be totally a waste of time. So and so let's go to this example where like the prompt is like Emily buys three apples and two oranges. Each orange costs $2, and the cost of the fruit, all fruit is $13. What's the cost of each apple? Now we generated 15 solutions. Only four of them were the right answer. Take the top solution, train on it, repeat many times. So this is a method of uh, reinforcement learning from human feedback. And so basically, how does RLHF work? So no, to in order to train these models, in order to give them the human preference way, we actually have another model. So basically, like an entire different model called uh, what's the name? So called a model of human preferences. So yeah, so fine tuning language models from human preferences. So we have another model which knows just about human preferences. So now these models give out uh, like like how you do like exactly the RLHF is that like you give it a prompt, like given a prompt, like you would give it may like millions of prompts obviously, but given one prompt, you will ask the model that you just did SFT and everything on that the model in question. You would ask it to generate like some 15 solutions. Out of those, you would rank four or five or just one as the right answer. Now, how do you define right? You define right by uh, using another model called models of human preferences. So, now how is human preferences? So, this model just knows about human preferences. So, there's no actual humans involved here, as you can see. So, as you can see, you will use humans. So that's the wrong spelling. So you would use humans to create a human preferences model. Okay, so your so whatever was created from base model to SFT model will now be trained using this human preferences model. Okay, so So where the training happens. So there's no actual humans involved here, and obviously now to take much less time to create a human preferences model and then train using this model rather than using humans directly. Now if you use humans directly, it would take a lot of time. It would take a lot of time. So and that's how you get like the final model. So base model, SFT, final model, and the final model. So it did by using human preferences model. So and oh yeah, so the person like Dario Amode, founder and CEO of Anthropic. So he's the one who he and his team, Dario Amode et al. When he was at OpenAI, created this wonderful method, which is now almost industry standard. Uh, Now it's fair to note that like most like pretty much all the concepts in AI like transformers and everything was mostly created in the Google team. So uh, various people working under Google, they pioneered a lot of these concepts, and also uh, yeah, of course, the legends of AI like Jeffrey Hinton, Ian Lincoln, and Ilya Sutskever and Ray Karpathy, Richard Sutton, and many other legends. They contributed immensely to this field, and so yeah. So once that is done, we you have the RL model, and that's it. That's exactly it. That is how you create an LLM. So just just to overview it again, you gather the data, and then you perform you tokenize the data because numbers is how the computers understand them, and you have the neural network training and using transformers, of course, and this base model will now get supervised fine tuning. So the pre-training is just going through the background knowledge for the student of LLM, the student called LLM. I mean, so the LLM student will now go through worked out examples, and you teach it how to answer questions, what not to answer, what to answer, what to do when it doesn't know how to answer, and then finally you ask this LLM student to perform tests and give it a test and make it better, uh, increase its performance in the real world tests. And that's it. That completes the overview.